Thank you. Our next speaker is Dr. Stephen Musolino. He is going to be talking about meeting the needs of first responders, scientific experiments, to operational tactics for the first 100 minutes after an outdoor explosive radiological dispersal device. Dr. Musolino is a scientist in the Non-Proliferation and National Security Department at the DOE Brookhaven National Lab. He is a PhD in health physics from the Georgia Institute of Technology and is certified by the American Board of Health Physics and is a fellow of the Health Physics Society. Dr. Musolino.
Thank you. So I'm going to spend some time today talking to you about how we take basic science and turn it into something useful and practical that meet the needs of our first responder community. I'm not going to fully elaborate on the tactics for the first 100 minutes because I don't have enough time and I have a number of other topics to cover. So I'm just going to give you a flavor of that and then just tie it into some other related issues. I do want to acknowledge some other people who have had contributions to many of all the topics in my talk, and that's Dan Blumenthal, Brooke Budemeyer, and Fred Harper from Sandia, and many others that I didn't mention. So this is the work of many people that have contributed to this over a long period of time. First off, here's the problem. Radiation protection experts do not routinely respond to emergencies and may lack the skills to support an emergency. There's a lot of smart people in the health physics business, but if an RDD happened tomorrow, that's a very specialized set of problems to solve, and the knowledge is some of it would not be readily at hand, and the first responders need it now. So they need sound scientific advice and planning, and they also need radiation protection experts during the event to assist with the actual emergency response. Likewise, one of the big problems we're solving is during a radiological emergency, there's going to be fear of radiation, lack of familiarity, and this adds complexity to the decisions and operations that have to take place. And the responders also have to manage their own safety. They're not going to have a radiation professional, there with them. They've got to do it themselves. And the responders, if they don't have this knowledge, they may delay essential life-saving and rescue operations that should not be complicated because of the presence of radiation. Okay, so it's 11 o'clock in your city, maybe right now, and an explosion happens. Well, if that happens, there's going to be a typical response of the usual first responders, police and fire, EMS, and so forth. Now, when they get there, like many other cities around the nation, most have radiation detectors with them. So presumably, shortly thereafter, they're going to realize this is not just an explosion; this is a radiological event. So this is now a very complex situation that's much more complicated. And so what do you do at this point? What are you going to do in the next 100 minutes to ensure that medical services are provided to the injured and the public is protected? Well, we have a project ongoing right now with 4 pilot cities in the U.S., New York, Philadelphia, Fort Collins, and Chicago. We're actually developing the concepts and the tactics to answer that question specifically. What are you going to do in that first 100 minutes? The first is to recognize that this event has occurred in the first place. It's not just an explosion. And then to make the proper notifications, because you've got to tell a whole bunch of different people that normally got notified that something bad happened, and get the radiological and other resources activated. And then to initiate a response to an RDD versus to a response to an IED. And then the hard part is to measure and map the footprint of radioactive material, what was the fate of the radioactive material after the explosion, and if this is all done successfully in a short period of time, to then quickly transition to a recovery phase. Now, we say 100 minutes, but it's not a standard. It's a concept, and it's an idea to really say that whatever you do in the first 100 minutes, you need to get it right. Because if you don't get that first 100 minutes right, it's going to be far more difficult to get into that recovery phase and also maintain credibility with the public. So these 5 missions are boiled down into 10 tactics. The 10 tactics are numbered. They're not in order of priority. As I've said, I'm not going to. I don't have enough time to just go through them one by one like we normally do with the Pilot City meeting. So I'll cover a little bit of it, but this is how it's broken down. Now, there's science behind all this. There's actually 25 years of science, and there's over 1,000 experiments that Fred Harper at the Sandia National Laboratory has done to understand how the material that you'd find in an RDD would behave in an explosive environment. Now, we know the materials that would end up in an RDD because we know what the NRC license is. So we know that if it's cesium, it's cesium chloride. If it's cobalt, it's probably cobalt metal. So and we know the quantities that the NRC licenses them in. So we have a very good idea of what the starting material is going to be and its chemical physical form. And Fred has looked at this every which way you can imagine in terms of different chemical and physical form, different device geometries. So we can make very good predictions of what the fate of the radioactive material is going to be after it is put in an explosive environment. Now, there's the scientific publications behind this are in the literature. Fred did publish a summary paper of the material science, and then we took his esoteric science and we turned that into plain language in the 2006 publication, and that was incorporated. That was incorporated into NCRP Report 165. Since then, Fred has done more experiments, and we incorporated the results of those experiments into a new paper in 2013. And also, let me acknowledge Chief Rich Sluick, who's a battalion chief in New York City, the fire department, who's here today he's in the audience today and part of SE 3-1. We also strive to make this material practical and usable and in the language of the first responders. And he's our reality check to make sure our scientists do that. So here's the problem we've been solving. There's a lot of bad information and a lot of incorrect information about what the consequences of an RDD might be. This was published 14 years ago in Scientific American. I could spend an hour explaining why that analysis is just completely incorrect and doesn't give you any of the right perspective. To this day, this kind of information still comes out in the scientific literature. I saw a paper that was published in the last year that was precisely the same analysis, and it was done by a nuclear regulatory agency for a country I won't mention. So, this stuff is out there, but then there's Fred's experiments. This is an experiment that was done with technetium-99. Most of his experiments are done with stable material, but this is one of the few experimental series. He actually uses real radioactive material and then goes out and measures it in the environment. So there's a more realistic prediction of what's going to happen to it in an explosive environment. So. Here's an experiment at Sandia to kind of make the point that you have to understand the science. Now, this bright spot here, these are ballistic particles that were shock centered as a result of the shock wave hitting the material in the experiment, and they're particle sizes of a few hundred microns. Now, also note that they're going vertically. And since they are relatively large since they are large particles, they're not going very far. So they're going to deposit very locally. Now, if there is aerosol produced that's going to be taken away by the wind, it remains in the fireball, either here or here. And these would be subject to the local meteorology. But in this case, you're making a fair amount of ballistic particles, and they're just not going very far. That's going to be a very local deposition. So to summarize 25 years of experiments, if there's small particles produced, they're in the fireball and they'll carry by the wind. Note this experiment here. Here's a similar amount of ballistic particle production, but they're going like this. So they're not going straight up. But regardless, this is going to be a very local deposition. And one of the other takeaways you should get by looking at these two images is the design of the device gets a vote. And putting a source term into a computer and running a model and coming up with a cigar is not the correct way to decide what an RDD consequence is going to be. And when you do the experiments and you build a database of information, then you can start to make realistic predictions of how the material is going to behave. So if aerosol is produced, approximately 5% of it is going to remain. 5% of the aerosol in the fireball will get deposited on the ground underneath the detonation, and that's an observable. That's a diagnostic, and that can be measured should this occur. So again, you can see the aerosol is going to be taken by the wind. Ballistic particles is going to be a local problem. So I can summarize this graphically, and this image here is to scale, and again, it's based on experiment. So if there is aerosol, there is a predictable size hotspot that's going to be on the ground. These are the ballistic particles and how far they'll go. You could get large chunks of material, and they're also going to get thrown, but they're going to get thrown a finite distance, and that can be estimated. And any aerosol is going to go with the wind. And to make it simple on the non-scientific community, we call ballistics BBs, and we call the aerosol smoke. So, did the device produce BBs? Did it produce smoke, or did it produce both? So, this is just to compare the scale of where the consequence is going to be. If you had a predominantly BB event, you're going to have deposition of the material on the order of just a few hundred meters around the event. Whereas if you did produce aerosol, then you can have effects at much longer distances. So again, just because you have some radioactive material and an explosion, you don't immediately jump to the conclusion that there's aerosol deposition at long distances. Although it's just one of the possibilities. And this is something that needs to be sorted out by the first responders very quickly in terms of field measurements. They got to decide which one of these events just occurred. We've also boiled down some a set of default hazard boundaries where we can issue protective actions with only knowing that there was an explosion, there's a radiation signature associated with it, and that's all you know. So again, from Fred's experiments, we know that if you're 250 meters away from the detonation, you're safe from the potential of an acute radiation exposure, either from radioactive material on the ground or from inhalation of aerosol. So that's an important starting point the first responders can use. To be protected from lower levels of radiation, 500 meters from the point of detonation and 2,000 meters downwind if you know the wind direction. That's another problem, that just because you go on nowhere and get the wind direction, that doesn't mean the wind direction at the time of detonation is the same wind direction, because you have all the urban micrometeorology issues to deal with. So but again, this is a summary of 25 years of science to make a simple set of guidance like this. So One of the other important pieces of guidance we stress with the first responders, which is counterintuitive from a nuclear detonation, where the national guidance says, go take shelter and hunker down until you know what's going on. With an RDD, based on Fres experiments, we know that if you're just going to go in and grab and drag and rescue people, that you're not at risk of an acute radiation exposure. So we tell them to do not delay any life-saving and rescue efforts, and to begin search and rescue immediately. Don't wait for a radiation instrument to arrive. Radiation equipment is desirable, but it is not required to respond to an RDD for life-saving. And again, there's 25 years of experimental science behind that, and it's just not a simple presumption on our part. So my personal point for this situation is that you can't model your way out of this problem. You can only measure your way out. And the initial data points collected can provide diagnostic information to make this determination. Was it BBs or smoke? And to pinpoint the locations of contamination, or more important, the lack of contamination, and also promptly rule in or rule out an alpha-emitting isotope. So, this is the tactical approach needed to get data for an analyst to make more informed decisions. So we've broken it down into a simple construct for going out and making field measurements. There's basically 4 pieces. The first piece is around the detonation site. The second piece is the near field in the prevailing wind direction, and then to do a transect across the assumed direction of the wind, and if needed, then make downwind measurements. And also the fourth is to do the outlying areas, because that's just as important to go out and find and measure zeros as it is to find the contamination footprint. Now, here's the scale of the event. There's the 2,000-meter box, but despite the fact that this is where the emergency phase is going to affect people in the environment, everyone here is going to believe they're probably going to die this morning and be in fear of radiation exposure. So getting this information here in terms of measuring background and mapping it and getting it to the media and decision makers is just as important as defining the radiation characterization of that box. So if there is aerosol, it's not going to be the world is not Gaussian, and it's going to be a chaotic mess of hot spots and cold spots. And only by collecting lots of field data and putting it on a map will you be able to get some fidelity on what this picture actually looks like. So to do that, as I've said, we've broken into four pieces. This is incident command system language. Strike Team 1 is assigned the detonation site to make measurements close in. Strike Team 2 does this transect here at approximately 1,000 meters, and this is a very important set of measurements, because if you make this measurement here and you find background, that's telling you I probably have a BB scenario. Now there's a couple other measurements you got to make to confirm that it actually was BBs or a dud, and you can't rule out the fact that the first couple RDDs we see are just going to be poorly designed and a dud. So this is a very early measurement to start to give you good situational awareness. Contrary to that, if you did do this measurement and you find contamination at 1,000 meters, then you know you have a smoke scenario, and you know that there's contamination at long distances, and your bad day just got a little bit worse. If that result is positive, then we recommend that this strike team continue on and make 8 additional points, which are the remaining parts of what the DOE responders are trained to do, and what we're asking them to do is to complete this 10-point survey. This data gets ingested into the DOE atmospheric model by the National Atmospheric Advisory Center in NARAC, and then NARAC will calibrate their dispersion model and be able to give a projection of the material on the ground. So this data is very important to the DOE response. Now, it doesn't have to be done by field teams. If there's radiation detectors in the vicinity, we can just call the local firehouse, a police precinct, and ask someone to go outside and make a measurement with their radiation instrument that they have on hand. And it doesn't have to be done, specifically. You just have to get close to these points. You don't have to get right. It's like horseshoes. You just got to get close enough. Strike Team 3 will work on the near field, again, gather data, and as part of the measure and map. The more data, and in this case, too, you don't need a lot of data. You just need the right data. And if you get the right measurements, you get them on a map, then you have visualization of the problem. Now, Strike Team 4 is a virtual team to, again, make phone calls, use the internet or whatever, two-way radios to collect radiation instruments from locations that already have them, like police stations and firehouses, hospitals, or whatever. And again, this is an issue of planning to have that in place. Now, here's a question. You get all this data. Who's the radiation expert to advise the decision makers on this? And this is a question we're posing to the pilot cities, and one that, quite frankly, they have no reason to have thought about this. So if you're Philadelphia, and the hazmat teams or whoever have gone out and collected all this data, some radiation expert has to then look at it and make a decision and give advice to the mayor, give advice to the governor, and anybody else who needs to understand just what the heck is going on at this point. So within 100 minutes, we need a qualified analyst to do this interpretation, and also behind them 100 minutes, there still needs to be this support for the transition to recovery before outside resources occur. So this is a challenge to the radiation protection community to have people available who can do this, on this kind of time frame. Well, one of the solutions to that problem is already in the works. It's called you've heard about it already a little bit today, the ROS. And this is a call to health physicists to join and become part of this cadre of people. And from what I heard yesterday, all or most of you in the room will be retired by the next meeting. So there's, maybe you can think about, next year becoming a ROS. So there's effort to try and get people to join this effort. Now I want to make a point that these are the type of people who will support the incident command system. They'll help access specialized federal resources before the federal resources get there. And they're the people who will help interpret and explain data, provide guidance to responders, and aid the public in responder communication efforts. I want to emphasize, too, the ROS is a state and local asset. It's not a federal asset, and they report and work in the best interests of the state. And they can be used throughout the response structure, but most effective as a technical specialist to the command staff. Now here's, if you're familiar with the incident command system, this construct will be familiar. This is where the ROS potentially could fit into the incident command structure. You could see a ROS at a command post, a ROS at the branch, but there's many places where this type of expertise is needed, and this function can serve that need. Well, let's just switch gears for a minute and ask the question, what if this incident was a nuclear detonation? A much bigger problem. But first, Fukushima has some lessons to this issue. By March 12th, this is what the shelter and evacuation looked like out in this region here. And that, as you know, happened very quickly and effectively. Well, it took a couple of weeks to get enough data to make the decision on the relocation based on the 20 millisieverts in the first year minus the emergency phase, and that happened a few weeks later here. Now, the bottom line is that ended up causing displacement of a very large number of people. And it's well known that this displacement of people, had a human toll in addition to the earthquake. And there were many fatalities that were indirectly occurred through this displacement of people. And the more notable one that many probably have heard of was moving patients from a nursing home that was about 5 kilometers from the site. Now, that's an issue where taking the radiation dose would have been the right action to do, but I'm not going to second guess the people who made this decision, but ultimately, that's what happened. So, again, this is where a role like the ROS is needed, because right after a nuclear detonation, despite the fact that there's enormous devastation from the actual blast and effects from the blast to a region around the ground zero, and there's going to be a lethal fallout cloud for a very long distance, this area around here is filled with injured people who need to be rescued, and people who need to get out, and people who need help. And this is where the first responders are going to put their efforts in the very early period after a nuclear detonation. And this is where they need advice and counsel from radiation experts in this early period. And the more expert advice they get, the more lives they're going to save, and the more human suffering they're going to alleviate. In the real world, to carry this out is complicated, because the federal data products, if you're not familiar with them, can be very complicated to use and to explain. And having a ROS there who understands them and can help communicate them to the emergency managers will go a long way to help in the incident. And being able to communicate the interpretation of the data and assessments will help shelter and evacuation, defining population monitoring and decontamination, defining where the hot zone actually is, and use of PPE, etc. So many radiation professionals are needed in this situation. Here's an example again of where radiation professionals are needed in decision making. The emergency phase criterion is 1 to 5 REM in the first 96 hours, but in this model of a nuclear detonation for the recent vibrant response exercise, you can see that extends out 160 kilometers. So are you going to recommend evacuation, at 1 REM in a case like this? Personally, I don't think so. But this is a very good example of where the decision makers need radiation professionals to help them, think through the implications of an evacuation on this scale, and where it's certainly the risk benefit is to rather have people take some exposure and wait a little bit while longer for the material to decay away. So again, this is an example of science being injected into a crisis, and the need for advisors to help interpret the science and explain it to people who may be dealing with radiation for the first time in their life. Here's another example of a complex decision. This is a plot of where the fatalities would be from this nuclear detonation. Now, clearly in this area here, it's of complete devastation. But then downwind, this is where fatalities would produce. People would be expectant in 30 days out in this region here. So again, this would be something where you'd have to make some very hard decisions on where to put resources and where not to put resources in terms of where the effects are taking place, and also fatality measurements. Again, radiation professionals are needed to interpret these sort of complex situations that will result from an event like this. So I'll end by asking the question, you know, where are the radiation professionals for emergency response? And just to add on to the previous speaker, I'll say, where are they for national security? We need them for the future. Thank you.